I wanted to show you all, if you look at problem number 3 on the back side, how you apply Kirchhoff's two laws of circuits to solve for the unknown values of the current. I call this my standard approach because if you simply follow this approach, starting at the same point each time, going around the same loops each time, labeling the currents the same way, you have a common set of steps that always will work. The numbers are sometimes rather odd in real circuits. They'll have, 4.239 milliamps of current. The currents can be negative if you have drawn arrows in the wrong direction and the batteries are pushing the current in the opposite way, but the technique always works. To use this technique, the first thing you've got to do is notice how to label your currents. Now my currents here have already been labeled for us. They've got I1 here, I2 over here, and I3 running down the middle. If you did the FET simulation, you would have seen that those three currents are different. And the big idea is that in this portion of the circuit, anywhere where these wires are running between what we refer to as nodes, here at the top there's a node, here at the bottom where three or more wires come together, the same current is flowing in any portion of this circuit. So I only need to label it one time, I1. I2 is flowing in this portion of the circuit over here. And I have decided, just because I can, to assume that it's going to be flowing in a in a clockwise way. I3 is going to be flowing downwards like this, and in this case there's only one resistor, but it's going to have the current the same above it, through it, and below it. Those three currents are the three unknown things that we're trying to solve for. Now in our work, what we need to do is to be able to apply Kirchhoff's laws to generate three equations to help us solve for those three unknown values. All right, so let's go ahead and do that. Now, a key idea is that when we start, we're always going to apply the current law first, and we do that at this upper node. That upper node has one current flowing into it, two currents flowing out of it. So when we write down the current law for that node, what we have to do is to sum up the currents flowing in on one side and the currents flowing out on the other side. So Kirchhoff's current law applied at that top node is going to be pretty easy. And if you follow this standard approach, it is always going to give you, every single time, the exact same answer. So when I apply the law, what I want to do is have the sum of the currents flowing in and set them equal to the sum of the currents flowing out. And because I only have three currents, that's very simple. And what I'll end up with when I do that is going to look like this. I1 flowing in is equal to I2 and I3 together flowing back out. You saw that in the simulation. Now, if I want to use my voltage law, I have to apply it to loops, and we always want to start at a common place. So that big dot shows me my starting point, and I always put it at the lower left-hand corner. It doesn't matter what the next component is. I'm always going to go clockwise around this first loop like that. So I'm going to call that loop number 1, and then I'm going to start at the same point. I'm going to go around the whole outside, and I'm going to call that loop number 2. So when I apply the voltage law, I have to go around complete loops starting and ending at the same point. For two loop circuits like this, these are the easiest. I like that also because you'll have two terms typically, the first battery and the first resistor in this case, that are the same between the two loops, and it gives you some confidence that you're doing everything correctly. Now when I apply this, I'm going to apply Kirchhoff's voltage law. I want to use a symbol to indicate not at, but around. So it looks kind of like that, but it is going around in a clockwise way. And I'm going to go on loop number 1. I'm going to do a little bit of abbreviation, if you don't mind. And the idea here is that when I add up the voltage drops for all of these components, from I equals 1 to however many are in that loop, I'm going to get 0. Now, I'm going to leave my 0 there, and I'm going to do the first loop on the other side of this equal sign there. First thing I encounter is a battery. I am going through the battery the correct way, so it boosts my voltage by 18 volts. Then I'm crossing a resistor, and that resistor drops the voltage. It's a 12 ohm resistor, and it has current I1 going through it. So I got minus 12 I1 like that. What do I see next? Well, I've got a 6 ohm resistor, but I've got a different current. So I have minus 6I3. Now, 6I3, where's that coming from? That's just V equals IR. This is my resistance R. This is my current I. So I've got them in opposite order, but that is a voltage drop. There's my negative sign to show you that it's dropping because the resistor is dissipating energy, whereas the battery is adding energy. Is that it? Yep, I'm done. That's it. Now, I got to do the same thing, Kirchhoff's voltage law, and apply it around in a clockwise way, loop 2. Now, loop 2 goes all the way around, and we're going to do the same thing. We're going to add it up. We're going to set them equal to 0. And I want you to notice, as I mentioned previously, that the first couple of components are exactly the same. And so our first thing that we hit as we go through this part of the process is that 18-volt battery again. And then we hit that same 12-ohm resistor. But then we deviate. Once we are in this portion, I2 goes through a 1-ohm resistor, and it also goes through a second 1-ohm resistor down here. So to save myself a little bit of trouble, I'm going to add those together right now. It goes through one, goes through the other. I2 is going through both of them. I've got a battery here. I'm going down through it the correct way from negative to positive. So it boosts my voltage by 12 volts. And then I'm home free again. In between here and here, there's nothing. I've already included that 1-ohm resistor. So I've got equals 0 like that. Now, to clean it up a little bit, all I got to do is add together my two constant values and add together my 1 plus 1 is 2. So this final equation, oh no, it's not going to be 18. It's 18 plus 12 is 30. And the 30 minus 12I1 is going to be combined with minus 2I2 to give us our final equation to solve our unknown values. Now typically we would number these. This is number 1. This here in purple is number 2. And this here is equation number 3. What I'm going to show you on the next slide is how you would solve for this. It's not too hard as long as you've had practice, but if you've never had practice doing this kind of thing, you might want to see some steps. I'm going to show you on the next slide the same equations. I've neatened the whole slide up a little bit, but what we're going to be doing is manipulating them to solve for I1, I2, and I3. So here we go. Now, number 1 was our I3. I'm sorry, I1. Made a mistake there. I1 equals I2 plus I3. There we go. Number 2 was our 18. We had minus 12 I1, and we had minus 6 I3, and that equals 0. And our final one here is also a number, 30 volts. We had our 12 I1 as before, and this time we had minus, let me check my notes, what do we have? Minus 2I2, there it was, and that equals 0. Now, in my standard approach, what I'm going to ask you to do next is simply to accept on faith that this order of operations always works. What I'm going to be doing is eliminating I3 in this equation by using the top one, and that will give me two expressions that have only I1 and I2 in them after I do this substitution. This allows me to combine the two equations to get rid of one of them. We're going to get rid of I1 next. We're going to make him go away. And the first one we're going to solve for is I2. All right, now to show you how to do that, I want to get rid of I3. So I'm going to use a manipulated version of this one to plug in to the second equation. So you can see that I3 is just the difference of I1 and I2. I'm now going to plug that in here. I'm going to do that down below. So when I modify number 2, let me show you what I'm doing. There's number 2. My 18 doesn't change. My minus 12 I1 doesn't change. And the next part, minus 6, I'm going to have to substitute in something. I'm going to put my parentheses there first. Here's my I1 minus I2. Now, that is going to equal to 0. If I combine like terms, what you'll notice is my 12 and my 6I1 combine together to give me minus 18I1. But here I've got to be careful. I've got a negative sign and a negative sign. So I don't have minus 6I2, I have plus 6I2. And what I want to do next is to remind you that in equation number 3, I also have only I1 and I2 showing. Look at that. So at this point, I simply pick another one to eliminate, and I have already designated I1 as my victim. So for number 2, eliminating I1, another way of thinking about what that means is solve for I1. And if I do that, solving for I1 with equation number 3, I'm going to be able to set them equal to each other, and as a result, I1 drops out, and we're going to get I2 first of all. So when I solve for I1 here, what I'm going to have is it's got a factor of 18, but I'm going to be dividing that out. And when I bring these terms over to the other side, I have 18 and I have plus 6I2. And what you're going to see is that when I divide up by the 18, 18 over 18 is 1, 6 over 18 is 1/3. In this particular problem, it's going to be easier to leave that fraction. I've already solved it, so I know this, but in general, you could calculate it out if you wanted to. If I do the same thing now with expression number 3, remember, I've already done this, so I'm going to let you try that on your own. What you'll end up with when you solve for I1 looks like this. I1 comes out to be 2.5, and there is a minus 1/6 I2. And when I set these equal to each other, effectively what I'm doing is I'm saying, hey, if you're I1 and I'm I1, we can set these sides equal to each other, and it eliminates I1 from those expressions, and you can get a solution for I2. Now, when I do this, I'm going to get 3 numbers. I'm going to get I2 first of all. I'm going to be able to plug that back into this third one, for example, to get I1. Then I'm going to be able to plug both of those back into the first one to get I3. When I do that, if you follow along in your own notes very carefully, you should be able to get the following answers. I'm going to pause the video and I'm going to type them in, and I want you to see by pausing it as you watch this video if you can solve and get the answers that will appear below miraculously. Here we go. Let me pause it and write down the answers. All right, there are the answers. Did you get those? I1 is 2 amps, I2 is 3 amps, and I3 is what? Negative. It is a negative 1 amp because in that middle leg of the circuit, when they assumed that it was flowing downward, they were wrong. The current is actually flowing up. The negative sign indicates that. So nothing is wrong. It's just that they have made an assumption that turned out not to be true. So negative signs give you information about the direction, the actual direction of the current flow. If we had drawn that arrow for I3 upward and done the work exactly the same other than that and solved, we would have ended up with +2, +3, +1. You'll get the same answer when you interpret it correctly, regardless of your loops. All right, next what I want to show you is a picture version of how you can solve the same problem using matrices. If you know how to do this on your calculator, it makes it far quicker and easier. If you don't know how to do it, just apply the standard approach. It might be a little tedious, but it always works. All right, thank you for your attention, students.